Hello, everyone. Thank you for joining in again. I'm going to talk today about thermodynamics, kind of in a very broad way. Give us some of the basics. I'm going to try to give us some of the basics of a lot of what we're going to see in the problems. The concepts here work best within the context of actually solving the problems. So it's not always going to be the greatest amount of detail on some of these, but I want to give you some kind of a feel for a broad range of basic topics pertaining to thermodynamics. So let's take a look at it. Let's go for it. Let's talk. I've already mentioned some of this stuff in other places, and obviously you're free to look at this stuff in other places too, and I hope that you do. But sometimes the repetition of seeing this again, maybe from a little different perspective, I think is going to help us out. With that in mind, let me start with the kinetic theory of gases. I'm drawing from the brilliant work of Surway and Vieul, College Physics, 11th edition, volume 1, pages 332 to 334. The Surway and Vieul book, the 11th edition, that's currently used for the non-calc treatment in the classes that I've taught. Non-calc treatment of mechanics. But it's going to help us in whatever the class is, whether it's calculus-based or non-calculus-based. Very, very much of this stuff is done in a non-calculus manner and gives us a lot of good background. So I think we're good no matter how we go about it. So it's from the Surway and Vieul book named College Physics, 11th edition, volume 1, pages 332 to page 342. There are a few things we're going to write down, kind of keep in our mind, and we'll kind of move around with this stuff. Try to cover a good amount of the material, guys, which means, how does that saying go? Jack of all trades, but a master of none. You look at all this, and you at least have some of the basics so that when you do attack the problems, you've got the machinery to attack a good portion of the problems that are going to occur across, 2 or 3 chapters at least. So good for us in that regard, I think. They talk about Avogadro's number, and let me just always check, make sure this is, you should be able to, I want to make sure everything can be seen, guys. They talk about Avogadro's number, which is N sub A, Avogadro's number, and that's the number of particles per mole. And, it's not something, obviously, I guess this is not a number you'd want to make up, because if you're looking to make up a number, I guess there's better looking numbers that make up, you guys. It's 6.02. It's 6.02 times 10 to the 23rd particles per mole. This thing called a mole has 6.02 times 10 to the 23rd particles present. The particles could be single atoms, or they could be combinations of atoms that are bound together to form diatomic molecules or polyatomic molecules. Numerous atoms put together to form a molecule of a particular substance or compound. Basically, the way they've got this thing put together is if you took hydrogen, which has an atomic weight of 1, and if you had 6.02 times 10 to the 23rd atoms of hydrogen, that would be 1 gram of substance. So they figured out a way that they could figure out, well, how much do you need to have 1 gram of a monatomic molecule that has each one of those monatomic molecules, or atoms in this case, right? Let's say it was a monatomic, let's say hydrogen by itself, even though hydrogen is a diatomic molecule. If hydrogen by itself has an atomic weight of 1 or thereabouts, 6.02 times 10 to the 23rd of those hydrogen atoms would give you 1 gram of substance. Therefore, if you took a substance that had an atomic weight of 92 times more than hydrogen has, there'd be 92 grams of the substance if you had 6.02 times 10 to the 23rd atoms of that substance. So this is a convenient way to say, okay, let's have 1 gram be the measuring stick. Give me something with 1 atomic weight. Give me the number of items with 1 atomic weight that would give me 1 gram of mass. Well, the number of those items is Avogadro's number, 6.02 times 10 to the 23rd. So that's kind of where it's going from. N is the number of moles. And if you take, based on what I just said, if you found the mass of the substance, typically in grams, it doesn't have to be. If you play this right, it works all the way around. The mass of the substance divided by the molar mass. So what's going on here? The mass of the substance, let's say that the substance has 92, let's say the substance had 92,000 grams of mass. And the molar mass is 92 grams, let's say, per mole. They write mole. It's been a while since I had that chemistry class, guys. It depends where. I think I've seen mass. I think they usually just write out mole. What I've seen more often than not to kind of play it safe. 92 grams for every mole. Yeah. Well, if there's 92,000 grams total, when you do the division, the grams cancel. You got 1,000 moles. Really? If you got 1,000 moles, how many atoms is that? Let's say this is a monatomic substance. Monatomic substance. It's not bound with anything. 1,000 moles. Each mole has 6.02 times 10 to the 23rd. 1,000 is 10 to the third. 10 to the third times 6.02 times 10 to the 23rd. The 3 and the 23 is 26. It's going to be 6.02. It's going to be 6.02 times 10 to the 26th atoms present, et cetera, et cetera. So, there's just a little bit of gymnastics they do here. You're going to have to take it on faith that they were able to find this thing out, and they go from there. There is the mass of an atom. And what is the mass of an atom? Well, the mass of an atom is, give me its molar mass. We talked about over here. Give me its molar mass and divide it by Avogadro's number. Well, let's talk. How am I going to know that's the mass of the atom? Well, the molar mass tells you. For example, the molar mass is 92 grams for every mole. Fantastic. Avogadro's number is 6.02 times 10 to the 23rd atoms. (6.02 times 10 to the 23rd atoms for 1 mole. Well, let's do the gymnastics, you guys. Atoms over moles flip, and you got moles over atom. The moles cancel out, and you end up getting the 92 grams over. There's 92 grams for every 6.02 times 10 to the 23rd atoms. So how many do you have per atom? Per atom, I guess I'd have to set up a ratio. Per 1 atom, what's the mass? I could do that. I could say, hey, wait a minute, there's 6.02 times 10 to the 23rd atoms. That corresponds to a mass of 92 grams. If I had 1 atom, which is 1 over 6.02 times 10 to the 23rd atoms as many. It'll be 1 over 6.02 times 10 to the 23rd atoms times this. Wait a minute. 1 over this times that is just this divided by that. That's another way. So you're going to get it that way anyway. Long story short, take this divided by that. It's going to be out of control, not a real big number. Let's see what we got here. Let me just kind of play some games here. 6 goes into here how many times? About 15 times. Let's see here. 15, a little bit more than that. I mean, not whatever. I don't want to split too many hairs, guys. The big thing here is, at least now, they're not asking us anything necessarily very specific, but let's just kind of do something here. It's about 15 times 10 to the negative 23. Yeah, I didn't expect the thing to weigh that much. I didn't expect that thing to have that much mass, and it sure doesn't, right? Go 6.02. 15.2823, so 15.28239, 15.2824, something like that. Just look at it carefully here. 15.2824, 2824 times 10 to the negative 23 grams. Kilograms, well, kilograms are 1,000 times more massive than a gram. So you're not going to need as many. So it's even smaller. If you wanted to go to kilograms, nobody asked you. But if they did, we've got the dexterity to know that's 10 to the negative 26 kilograms per atom that has a molar mass of 92 grams per mole. Okay. So there's a lot of there's a lot of monkey business they do here. It is completely justified if you're willing to believe that they were able to find out the significance of the number 1 mole being equal to 6.02, roughly 6.02 times 10 to the 23rd particles. Okay, so that's some of what's going on here, guys. There's a lot. I'm going to try to give you, like I said, there's always much more to be said. That, I don't care, and there's countless brilliant people out there who are going to know much more than I'm ever going to know, Countless brilliant people out there, and even the most brilliant people who are out there in mathematics and physics, they don't know everything, and they're not able to learn everything. They don't have the time. There's so much out there, But I want to give you at least some of the basics of what's happening here, so when we get some very, very good problems, very useful problems that can help us in all kinds of fields, from engineering to the medical profession to just to many things that go on in physics, very practical applications. And they're challenging problems, very good problems. I think if we got the basis, really gives us a stepping stone to move on. Nobody's going to know everything, and you're not going to have the time to learn everything, but you give it your best shot, and we learn as much as we can. That's the goal always when we're doing this kind of stuff. Okay, so we've said something here. So let's see what we can keep saying, I guess. Well, see exactly what I want to say here, guys. I mean, there's so much that can be said. Let's pick our battles and see what's going to be really useful for very many practical circumstances. They talk about this, and like I said, guys, I talk about much. You're going to see this in a lot of different books. At the basic level, depending upon the book that you get, there's some great books out there. And we're fortunate to have access to a lot of those great books. At the practical level, whether it's calculus-based or non-calculus-based treatment, you can get a tremendous amount out of either book. So I can use this for either class, for a calc-based class or a non-calc-based class. So, and we'll, like I said, you can kind of pick and choose. I mean, if I do go into calculus a little bit and it's a non-calc-based audience that's looking at it, don't worry about it too much. Just know the end result of what I'm doing. But there's so much useful stuff here, you guys, when we're doing this. They talk about the ideal gas law. And there's a lot that can be said. There's a lot that does get said. There's a lot of technicalities you can get into. A lot like Bernoulli's equation, where there's limitations to it, but it still has some broad applications to visualize much of what's going on. It seems to be that way as well with the ideal gas law. The ideal gas law, all the particles are point particles. They're point particles. They don't, I guess you could say, they don't collide with one another. They don't interfere with one another. And they're bouncing perfectly elastic collisions everywhere they are when they are in a container, if it's a gaseous substance. Monatomic point particles and how they behave. Now, you can model other circumstances that are non-monatomic and still make arguments for being able to use the ideal gas in a lot of circumstances. When the molecules get more complicated, there's different kinds of spin that they can have, and vibrations can take place, and all of that kind of has to be taken into account when you're talking about the energy of the system. Usually when you're talking about the energy of the system, if not always, we're going to a microscopic level when we're talking about a lot of this stuff, you guys. But at the microscopic level, there's still motion. And we know the faster that something is moving, the more kinetic energy that it has. If it is a molecule composed of multiple atoms, or even just two atoms, there is a spring associated with it, sort of. There's a spring, there's compression, there's stretching, and with that vibrational motion and stuff, there's energy stored in various ways associated with that. There's energy considerations that we have to bring into play with that if things get more complicated. When something rotates, it's not just that something's moving in a translational sense. If I roll a big boulder down a hill and it's not slipping, it's rolling, there's kinetic energy, so there's translational kinetic energy associated with it, but there's more than that. There's rotational energy associated with it. Another boulder that, let's say, slid right down the hill was just as massive, and it slid right down the hill. It was every bit as massive, but this one just slid down the hill, didn't rotate at all, and it went down the hill with the same translational speed as the other boulder that was rolling, let's say. There's more energy associated with the rolling boulder because it's not only got the same translational kinetic energy as the non-rotating boulder, but it's also got the rotational aspect associated with it. What does that mean? If you want to heat up a gas that's a very complicated material, there's a lot that's going to happen. There's a lot that's going to happen. You're not only going to increase its translational energy, its translational kinetic energy, there's going to be rotational aspects of energy that have to be accounted for and vibrational aspects of energy that have to be accounted for. That's going to be a lot harder to do with a monatomic molecule that maybe has the same mass as that molecule, but the only thing you're worried about there is translational kinetic energy. The other one, you're worried about translational kinetic energy and a whole bunch of other things. The more translational kinetic energy that is present is indicative of the temperature. A high temperature environment means for a gas, let's just stay at the level of gas, guys. There's a lot of what ifs and there's a lot of trees and a lot of forest I guess we can go through here. Let's just keep it at the level of a gas. If a gas is flying around and the average kinetic energy of the particles is very great, its temperature is very great. If the average kinetic energy of the particles, on average, of each particle, you're not going to change the amount of material that's in there, the number of moles or the number of, capital N is the number of atoms, and small n is the number of moles. And obviously, a lot of moles means a lot of atoms. A lot of atoms means a lot of moles, so they're directly proportional to each other. Small n and big N. If there is this, there's an average, nothing has changed, you haven't done anything, the volume is what it is, and whatever's going on here, stuff, and say, okay, here we go. I got a set volume V, capital V, and there is an average kinetic energy per particle of n moles of capital N particles, and that doesn't change either. There is an average kinetic energy there. It's very hot. There's a lot of temperature. Big temperature is indicative of a lot of internal energy. It's a lot of internal energy, and that internal energy is manifest in the high temperature. The higher the temperature, the bigger the internal energy. And let me kind of say very, very similar to that. The higher the temperature, the greater the average kinetic. If the average kinetic energy is great per particle, it's indicative of a high temperature. Absolute temperature scale. We don't care about Fahrenheit. We don't care about Celsius. We could make up another temperature scale if you'd like, but it's got to be an absolute zero temperature scale. It doesn't have to be the Kelvin scale. It could be another temperature scale. As long as there's an absolute zero. We'll get into that in a little bit. As long as somehow there's a zero. There's like a real zero. Like you can't get any colder than this. Period. There is no vibrational or translational or rotational motion occurring at absolute zero. Any absolute zero. Make one up or use the Kelvin scale. But 0 degrees Kelvin, 0 Kelvin, there is none of that. No translational motion, no rotational motion, no vibrational motion. It's done in that regard. They're just there. That means there's no pressure because the collisions that are taking place against the wall are what generate the pressure. It's all going to basic stuff that we've already talked about. Momentum, conservation of momentum, motion. Even at the microscopic level, we got to talk about motion, and it explains a lot. If the temperature, absolute temperature scale, let's say the temperature is 400 Kelvin, there is an average kinetic energy per particle that is very significant. If you cut that temperature in half, from 400 Kelvin to 200 Kelvin, half as much absolute temperature is indicative as half as much kinetic energy per particle on average. You can't do that with Fahrenheit. You can't say, oh yeah, it's 100 degrees Fahrenheit outside. Yesterday it was 50 degrees Fahrenheit. It is twice as hot today as it was yesterday. No, you can't tell me that the kinetic energy, average kinetic energy in this box that was at 100 degrees Fahrenheit, the average kinetic energy of the particles there is on average twice as much as the average kinetic energy as the particles that were at 50 degrees Fahrenheit. 50 degrees Fahrenheit, there is an average kinetic energy in the box. 100 degrees Fahrenheit, there's another average kinetic energy in the box, and definitely there's more kinetic energy in the 100 degrees Fahrenheit box compared to the 50 degrees Fahrenheit box. True, but it's not on average twice as much kinetic energy per particle. It's not scaled that way. But if there is any kind of absolute zero, you can even make one up, I told you. But you got to have an absolute zero. There's got to be a zero, a real zero where there's no negative under the zero. It's zero. If you've got it scaled like that correctly, it doesn't matter. It could be Kelvin or anything else for that matter. If the two temperatures have the ratio of 2 to 1, the average kinetic energies are at a ratio of 2 to 1, with the hotter having the higher kinetic energy on average, and the cooler, the higher temperature having the higher kinetic energy, the lower temperature having the lower kinetic energy. This is kind of a real classic equation that gets used a lot. And again, I just want to give you the basics. So when I do a few of the problems, guys, and you see them, it's like, okay, we've seen this before. All of this I have on, everything here I also have on Canvas. Practically everything that I'm saying, well, not exactly everything, but much of what I'm saying is going to be on Canvas, and the rest is in the book. When we say this, I mean, even in less than ideal circumstances, even less than the ideal gas law involved, this has wide-ranging applications and gives you a lot of insight, and there's a lot you can do. There's very much that you can do. This thing right here, I guess you can, and the temperature's got to be an absolute temperature scale that I've been talking about. If you divide by V on each side, if you were to divide by V on each, R is the universal gas constant. We're not going to make a big deal out of that constant, guys. Just know that it's a constant. It works. We can work with it. There's a lot we can do. Look at that right there. Well, with this right here, you guys, the pressure that will occur, and I'm sort of putting the carriage in front of the horse, you guys. You're gonna see why this is kind of a really big deal, and we'll talk about it again. But I'll tell you something. If the substance, let's look for a great pressure. A great pressure, where does the pressure come from? I'm coming right back to the old-fashioned collisions we were talking about on a macroscopic scale. Let's go to a microscopic scale. Temperature plays a huge role in what heat, regarding how we talk about heat, how we talk about thermodynamics. Thermo, warmth, something like this, warmth, dynamics, dinamika. Dynami is power, strength, motion. So motion of heat, motion of temperature, transfer of heat, things of that nature. How heat is talked about is where we got the thermodynamics coming from, guys. The pressure comes from the old-fashioned collisions that we're used to seeing at the macroscopic level. When microscopic particles collide, they exert a force. When they collide with a lot of other things, they continue to exert a force. I guess the faster that they're going when they collide, the bigger the collision. The more bam, the more hit that's going to happen to the wall, it's going to be more pressure. Force per unit area is pressure. Force per unit area is pressure. So when they collide, the faster they move, the more that's going to affect pressure. Yeah, I already told you though, when something's moving very, very fast, it's a microscopic particle, that's indicative of having a high temperature. Temperature and average kinetic energy of particles are directly proportional to each other. High temperature in the system means on average the particles have a high kinetic energy. Low temperature in the system means on average the particles have a low kinetic energy. Temperature and kinetic energy are directly proportional to each other. If that's the case, we know if everybody that's in there is moving really, really fast while they're colliding against the walls, if they're moving really, really fast, that's a great amount of kinetic energy. Great amount of kinetic energy, as we said, temperature, absolute temperature is directly proportional to KE translational. Directly proportional to kinetic energy translational, you guys. Okay? So, huge temperature, it's going to make the pressure bigger for a given amount of substance. True. R is a constant, so don't even worry about it. It's there almost like a placeholder for us. If the number of particles is very big, the number of particles being very big means the average kinetic energy of each one of those particles being very big, and there's many of them, means the collisions are all going to be pretty violent, pretty strong, so to speak, and there's going to be many collisions because there's many particles. So if you have, and that's just a constant, if you have a high temperature, that's a lot of kinetic energy on average per particle, and if you got a lot of moles, that means a lot of particles. There's a lot of particles and great temperature, it's going to be a lot of pressure. Yeah, I got another thing you can do. What if you make the volume really small? Man, they don't have a lot of places to go. They're really going to collide a lot. There's not a lot of distance they got to travel to make a collision with the wall. So it's inversely proportional to the volume. From there, you can multiply by V and get this, which is maybe a little easier to remember. Either one's pretty easy to remember. But that's where it comes from. Pressure's kind of the big measuring stick, force per unit area. How are you going to get a big pressure? I'll tell you how you're going to get a big pressure. We had a pressure here, for example. Call it P1. It had N moles in it. R stays the same. There's a temperature T1. And here the volume is V1. All right. What would the pressure be? That's scenario 1. What would the pressure be if you increase the number of moles by 10 times? I put 10 times the particles in there. I put 10 times the number of particles in there. R stays the same. Yeah, I did more than that. I doubled the absolute value temperature. I did even more than that. I also managed to take, I could leave the 1 there. This is not a big deal, you guys, but let me by the way, I also made the volume 1/3 of what it was. Are you telling me if you make the volume 1/3 as big as it was, man, what it tells me is there's going to be 3 times as many collisions. If you make the volume with the same amount, let's not even worry about different, there's a lot going on here differently, but let's say you kept the same amount of substance in there, N moles, and you kept the temperature the same, T. If you just changed the volume and scrunched it down and made the volume 1/3 as much as it was earlier, it's telling me the same exact collisions might be going on. You kept the temperature the same. So the kinetic energy is the same. Yeah, same amount of particles and everything. Yeah, but they got 1/3 of the room to move around without a collision. They're going to collide 3 times more often. 3 times more often collision is going to be 3 times the pressure. So this will flip over and make it 3 times the pressure. Yeah, if you double the average kinetic energy and also put 10 times of those, P2, here's 10, here's 2, that's 20. 2 times 10, 20. Divide by 3 pops up. So 2 times 10, the 3 pops up. 2 times 10 is 20, times 3 is 60. 60 Nrt over V. Wait a minute, what does that mean? Well, this is the original one. This was P1. That was P1, the original. 60 times P1. P2, let's just hypothetical here. I'm not going to get into all the practicalities of how strong the material's got to be and. That's not our problem. Right now, it's not our problem. We're doing a mathematical mind experiment here, and we're trying to see where the whole thing's going to go, how the whole thing plays. Yeah. Let's say it was possible. Let's say everything's reasonable, and everything else. 60 times the pressure. You better believe it. You got 10 times more atoms. They got kinetic energy double what they used to have. And there's 1/3 the volume present, which means they're going to collide a lot more often. So on and so forth. So this thing plays a big role. And it seems like if you're gonna do an argument regarding temperature, regarding volume, regarding pressure, you almost got to say how's the kinetic energy affected, if it is or not, and how's the pressure affected given all these other things that could happen. Increase the number of atoms, increase the average kinetic energy, in other words, increase the absolute temperature scale, make the volume smaller, et cetera, et cetera. So this plays big. If you multiply by V, you get right here. And I'm sort of putting the carriage in front of the horse. I've already done this lecture elsewhere where I did it a little differently. So when you see the other lecture in thermal process, I think it's in the lecture Thermal Processes, I'm sort of playing that game, and we come to here in a sense. We end up coming to here, or at least we're here anyway, guys. This is something that can be experimentally verified. Our common sense, I like to not say anything's obvious, but some things are obvious. Perhaps at some level, given the basis of the physics that we know, the base that we have at our disposal, our knowledge base, this is believable. And it can be confirmed experimentally. If it's confirmed experimentally, bam, we can get to that. I mean, obviously, if you get this, if you multiply by V, it becomes a simple mathematical operation to be right there. Shouldn't be an issue. Okay? So on and so forth. And there's a lot that gets said. Let me try to say some stuff here, guys, and see how you feel about it. Okay, so there's a lot to be said. You've seen it. You've seen the stuff, guys. There is the constant, and again, through experimentation, there's a lot they can say. 8.31 joules per mole, MOL, K. Degree Kelvin. It's not really a degree measure, but it gets said that way. I don't think anybody's going to nickel and dime you on that. Okay. So 8.31 joules per mole per Kelvin. N is the number of moles. How do you find that? Well, capital N is the number of atoms that are present, or number of molecules, whatever. And this is Avogadro's number. Look, let's get it straight. If there are 6.02 times 10 to the 23rd molecules present, and Avogadro's number is 6.02 times 10 to the 23rd molecules per mole, 6.02 times 10 to the 23rd divided by 6.02 times 10 to the 23rd, that's 1 mole. What if this is, I think it's a different number, man. I think the number is 10 times 6.02 times 10 to the 23rd over 1 times 6.02 times 10 to the 23rd. Well, 10 times 6.02 times 10 to the 23rd is 60.2 times 10 to the 23rd. And this right here is 6.02 times 10 to the 23rd. When you divide them, the 10 to the 23rd cancels out, and it's 10 over 1. 10 moles. That's all it's saying. So that's the number of moles. Well, okay. There's a little bit of gymnastics they like to do here, and we'll do it as well, I guess you could say. We know this. We can look it up. They can give it to us. It's not the big deal. We got this, and that's the number of moles. And they kind of make up a constant, and I guess I'll kind of get to that when I need to get to it. You've already heard me talk about PV equals Nrt. Well, let's just write it down again. And is it true that small n is capital N, the total number of particles, divided by Avogadro's number? All right, we already delivered that speech. RT. Then they leave the capital N like that, and they go R, which is a constant, divided by another constant. So, all right, let's see what we got here. Let me write it a little larger maybe. Guys, I'm always a little apprehensive on the quality of this thing as far as like audio visual. That's Na on the bottom. Let me just try to see what I just did here. Okay, right. I just took Na into R, and I got T. I also had T right here, okay. This R over Na is K sub B, constant called K sub B. That's R over Na. What the heck is that? Well, what the heck of that is this. This is 8.31. This is 8.31, and this is 6.02 times 10 to the 23rd. So when you do the division, it's 1.38 times 10 to the 23rd joules per Kelvin. I think at the end of the day, the way that thing goes. I think the moles cancel. You're taking this into the other one, and the other one's got R's got moles on the bottom, and this has got particles here. So they try to be a little careful on this. There's actually particles are present somewhere in here, but they don't really mention it. Let me not go down that path right now. This is joules per Kelvin. All right, so what does that mean? That means all of this. That means PV equals capital N times KBT. What is going on here? Why are you even going there, you might ask? Because this puts it strictly in the realm of particles, number of particles. You are explicitly mentioning particles, the number of particles present in the volume. In a particular volume. The number of particles present, capital N, and this is KB, and that's T. So that right there looks like this, and that right there looks like this. So they are identical. One's a little more macroscopic in character, one's a little more microscopic in character, but you're talking about motion. Why are you talking about motion? Because for there to be a pressure, there's got to be collisions. And for there to be a temperature, there's got to be kinetic energy. There's got to be motion. So everything we talked about in the past is alive and well, even here at this microscopic level. And much of the physics that you used for the big stuff, you're going to use for the small stuff. A collision's a collision. So that right there absolutely looks like that right here. So this is some of the stuff we're talking about vis-a-vis that stuff, you guys. Vis-a-vis everything that we're talking about. Okay. Ideal gas composed of atoms or molecules all making perfectly elastic collisions essentially equally against the side of a container, thereby creating the pressure which is manifested. Yeah, I say that in my notes. You'll see it. I've already gone into this, like I said, in another lecture. Let me kind of go into it again, say something, I guess. Make a couple statements, I guess you could say, and then see where we want to go when we talk about this stuff, you guys. Just arguing with myself how you want to kind of look at this and how this all plays out and what we can say. There's a lot that can be said. Let's say as much of it as we can, I guess, in a manner that's efficient and not too overwhelming when people look at it. Okay, you see all this stuff, guys. We're going to use the reality of this stuff in many regards. And let's actually almost, I don't want to say direct, I'm going to say experimentally this is verifiable at a macroscopic scale. And I talked to you about that earlier in this discussion. I believe it's reasonable. The thing that really calls the shots, or one of the things that calls the shots, is how much temperature is involved. If the absolute temperature is great, the pressure is going to be great, all other things equal. If the temperature is dropped substantially to a fraction of what it was earlier, the average kinetic energy has dropped then per particle on average. When the average kinetic energy was great, the temperature was great, the absolute temperature was great, the average kinetic energy of the particles was great. When the absolute value of temperature, when the absolute temperature drops, pressure is going to drop. All other things equal. When the absolute temperature goes up, the pressure goes up. Double the absolute temperature. You're going to double the pressure, all other things equal. Make the absolute temperature 1/10 of what it was, the pressure will be 1/10 of what it was earlier. And that's what I was drawing earlier, you guys. I erased it when I said P was equal to nRT over V. Okay. With this in mind, let's see what we can do. All right, well, let's talk about something that makes this believable, I guess you could say. Or at least much of this makes much of this believable, we hope, right? As we said, an ideal gas composed of atoms or molecules all making perfectly elastic collisions essentially against the sides of the container, thereby creating the pressure which is manifested. Given how random things are, all the collisions, roughly the same amount of collisions take place on any given area. You want an area that is 1/10 the area of the container? On that 1/10 of the container, 1/10 of all the collisions are going to take place on average. On another 1/10 part of the container that's 1/10 as big as the area of the inside of the container, another place is 1/10 the area of the inside of the container, 1/10 of the collisions are going to take place there. Go to the top or go to the bottom, collisions are going to be equally spaced, so to speak. There's a lot of symmetry into what's going on. That's the assumption that's being made. Well, let's say there's a box, but it doesn't have to be a box, guys. This could be a circle. This could be a sphere. It could be a cylinder. It could be something very, very bizarre looking as a container. It's like, wow, there's no symmetry to this thing at all. Doesn't have to be a sphere. Could be a sphere, could be a cylinder, could be a box, a rectangular box, could be a square box, which is what I'm going to use now. But it could be something totally amorphous, and the mathematics still works. We can kind of talk about that when we'll cross the bridges as we want to cross them. If you had square box, that's D length, that's D length, that's D length. And everything's just bouncing all over the place. Now, I'm thinking, here are the assumptions they make, guys. If there are a capital N number of particles in there, you can assume that on average, at any given time, 1/3 of the particles are going back and forth along the x-axis, or parallel to the x-axis. 1/3 are going parallel to the y-axis, and another 1/3 are going parallel to the z-axis. Roughly speaking, at any given time, of all n particles, 1/3 of them are colliding on the sides associated with the x-axis, another 1/3 are colliding with the sides associated with the y-axis, and another 1/3 are colliding with the sides associated with the z-axis. Well, let's say something's going back and forth and it's colliding. I want to we've got to be really careful on this one. There's a collision here. Let's look at one particle. Bam, it hits this guy. Okay, it hit him. It hit him. It did something. It hit him and it bounced off. And that collision, how to say it? That collision bam, it hit, it bounced off. It generated pressure. Okay, I'm not going to worry about that right now. It hit, it's going, it's going. All right, it hit once. And it's going to go here, a distance d, and then come back and hit again. I got to be careful how I'm going to talk about this. I want to talk about just one wall and just one particle hitting that one wall. What does that mean? That means it hit here, something happened as far as pressure is concerned, because the collision created a force was manifested. Force per unit area is pressure. Good enough for me. Well, right when it bounced off of here, it went this way, came to here, bounced again, and came back here. I'm going to worry about the second collision right here. I'm only worried about this side. The change in momentum. And I've got this, you guys, I have this. I have this on canvas for you guys, so you'll be able to see it as well. You can read it out. But MVX, this guy's, let's see what he does. I mean, he comes here. What's the collision? I mean, we can do a whole bunch of stuff here. Let's go that way. He starts here, but I'm not going to worry about that. He collides here. A collision happened here. Okay, I don't really care. I care that it takes some time for him to get over here and have a collision happen. Then he collides, it comes here, and he comes back. So what's going to happen is, right when he hits, he goes here, and then bam, comes back. He collides going momentum MVX, and he leaves also with magnitude momentum MVX, but it's negative. You've got to put the negative there. Because if you go MVX minus MVX, you got 0. And we know there is no way there's no change in momentum. This guy had a lot of momentum going here. He had a lot of momentum going here, and he had a lot of momentum going back. He had a lot going here, and he had a lot going back, magnitude-wise. MVX is this. Negative MVX is that. So you do this, which is equal to 2 MVX. The force for particle 1 is the change in momentum divided by the change in time. Well, the change in momentum, ladies and gentlemen, with all that went on here, it went here, then it went there. Okay? And then came back. I mean, he hit once, and then he's going to come back. So let's be careful. Let's be very careful. The change in momentum. Now here's where we got to be extremely careful. True. Okay, guys, so check my microphone periodically. I don't want it to go down, to go south on me here. Okay, what's delta T? Here's where you got to be careful. How much? I'm only talking about one particular wall at a time. Yeah, there's 6 walls there. I get it. There's wall on the left. There's wall on the right. There's wall back. There's wall in front. There's wall up and there's wall down. I guess they're in pairs. I get it. I'm going to do one wall at a time. I'm assuming there's symmetry everywhere. Everybody experiences the same thing for every wall experiences roughly the same thing per particle, certainly in the big picture with many particles. Okay. If that's the case, what is delta T? Well, delta T, let's figure it out. This guy goes here, bam, hits him. Okay, there's one collision. Got it. One collision happened. When's the next time it collides? Here. When's the next time it'll collide right here, or at least on this wall? It doesn't have to collide exactly on the same place in the wall, but it's going to collide on the same wall, roughly speaking. Well, here we go. Flies, bam, hits. He collided. Really? Yeah. How long did it take? Well, it took the time it took to go. He flew off earlier. He flew off from here all the way to here. Then he flew back. He hits. Then he goes here and then flies back again. He goes a distance of 2d. He goes a distance of 2d between collisions. Isn't distance divided by speed going to be time? I made it to this place 500 miles away. I was going 50 miles per hour. The distance, 500 miles, divided by 50 miles per hour, told me it took me 10 hours. That's all this is. The 2's cancel. The Vx flips up. And you got that. Whole song and dance. All the way to here. Okay? Now, I got some fancy footwork to do, I guess, on us. We know that the total force being exerted on any particular wall is F1 plus F2 plus ... plus F sub n. It could be a real big number. True. Yeah. F1 is equal to this guy, which is Vx, or V1x. V1x squared. M V1x squared over D will give you F1. The total force, well, all the particles have mass m. And the distance, d, is d. That don't change. These guys right here might be an issue. Let's put V1x squared, V2x squared, plus ... V sub n x squared. I wrote a little differently in my notes, but nothing major. Nothing major. This is for one molecule. And yeah, this is for many. A huge number of molecules. Yeah, I got to talk to you. If you put a bar on top of something, it's the average. I want the average of all the squares in the x direction. Really? Yeah, average of the squares. I'm not saying find the average and then square it. I'm saying take the average of every square quantity. That's squared. This guy, squared. Plus ... Yeah, I'm going to add all the squared quantities. I'm not squaring the result. I'm adding the squares. Then I'm going to get the square root of the average of the squares, and they call that the RMS, root mean square. Right now, let's just average all the squares together. And that's where we get this. Okay. What does that mean? That means a lot of stuff. I mean, you can say yeah, how do you get all this? How do you get this guy all by itself? Multiply by big N on each side. Yeah. The average of all the squares times the number of items. The average of all the squared velocities times the number of items that had those velocities, or from which you drew that conclusion, better put. True. Okay, that's true. Then F, now again, we already said yeah, that's F. Fine. Is there another way to write it? I guess you could say, well, we know a lot. We know that this is what we got here. Let's talk. What you're going to do is you're going to say F is equal to m over d. This right here is capital N times v sub x squared bar on top. That right there, this right here, is that, which is equal to that. Let's go with that. That's going to be m over d times n vx squared bar. Well, aesthetically, is there maybe a better way or something? Capital N so let me kind of give myself a little more room. Okay, guys, I want to make sure it's seen. That's the thing. I'm sure it's going to be, but so you're looking at this right here. All you got to do is, I guess, put the N in front of that. Okay. Yeah, pretty important conclusion. N times v sub x squared bar is equal to the sum of all the squares. The sum of all the squares times m over d is force, because this is for a single. And if you just put a lot of v sub x's there, it's the force for very many. And that's what this is. And this right here is the same as the average of all of these times n. It's coming to here, coming to there. So, okay. important consideration. So now, again, let me come back to things that we have said. The big thing, I can't emphasize this enough, you don't want to make this mistake of saying the distance is d. The distance is d if you're talking about two walls. I don't want to go there because the pressure is determined by a specific area being divided into a specific force associated with that area. You could do it with two areas, but there's half as many collisions, I guess, or you could say there's twice as many collisions, but there's also twice the area. So it wouldn't be different than this. You're better off just keeping the bookkeeping, saying, bam, this thing flew from somewhere and hit right here and bounced off. Okay, something happened. A collision happened. When's the next time it's going to happen? Well, he's going to go all the way to here and come back and have it happen again. When it happens again, he's going to go all the way over here and then come back and have it happen yet a third time. So 2D is the big one. 2mvx divided by 2d over vx. 2mvx divided by the ratio 2d over vx. And that's where we're getting this. And expand this to many particles, that's where we got this. The average of all of these is this guy. Multiply by n, you got all these again. So n times v sub x squared, bar on top of it, that's all of these. And that's what you put right here. N times this gives you all of these guys for all this to happen. And that came from here. Okay. Again, we're going to emphasize something. In the randomness of what's going on, we're not going to worry about what gravity can or cannot do or whatever. We're thinking, ideally speaking, let's say we're in an environment where there's no gravity anywhere. No gravity, and these things just bouncing everywhere because of the energy associated with what they're able to do. Doesn't have to be any gravity present. You almost make that in a backhanded way. You almost have to. You can probably argue this a number of ways, but I mean, I think you kind of make the assumption gravity's not going to play a role in this, so everybody's equally likely to hit any one of the 6 walls. What does that mean? That means on average, at any given time, a third of them are going along the x-axis, a third of them are going along the y-axis, and a third of them are going along the z-axis. Capital N is all of them. N over 3 are parallel to the x-axis in their motion at a given instant. Another N over 3, another 1/3 of it. So 1/3 are along the x-axis, 1/3 along the y-axis, and 1/3 along the z-axis. True. Yeah, because the motion is random, you guys, we could say a bunch of stuff. There's a whole lot going on here. You could say that also this could be a particle that has a Vx component of velocity, but it also has a Vy component of velocity. It also has a Vz component of velocity. And on average, all its components of velocity are equally distributed in the x direction, y direction, and z direction, even for each individual particle. The one particle that's doing a lot of work in the x direction, that same particle can end up doing a lot of work in the y direction, can end up doing a lot of work in the z direction. So its component, this is just its component of velocity that we're seeing. There's a lot they're kind of throwing at us, guys, and they're kind of like just throwing it right by us, and that's probably about the only way you can discuss this a little bit, but I want you to kind of see that. This could be, for any given particle, what's going on here. Well, you see what I can say here. So any given particle has all kinds of components of velocity, actually 3 of them. V sub x, V sub y, and V sub z. And we said all this, okay? We got all this. All right, so let's keep going. Okay, so what's going on here? Well, you can say probably number of interpretations, I guess you could say here, guys. Here comes the Pythagorean theorem again. For any given particle, its x component of velocity, the magnitude of the x component of its velocity squared, plus the magnitude of its y component of velocity squared, plus the magnitude of the z component of its velocity squared, gives you the square of the magnitude, the square of the total magnitude of its velocity. On average, the average velocity, just put a bar on each one of these guys, if you allow me to do that. Because the motion is random, on average, over the course of maybe a long time, the average velocity, the average of the square of a particle's x component of velocity, the average of the square of the magnitude of the x component's velocity, try to say that 9 times, right? Say that 10 times really quickly, I guess. Let me just say this. Hopefully I can kind of untie my tongue on this one. The average of the magnitude of the velocity, the average of the magnitude of the velocity in the x direction, the average of the square of the magnitude of velocity in the x direction is equal to the magnitude of the square of the magnitude of the velocity in the y direction is equal to the magnitude of the square of the magnitude of velocity in the z direction. Because it's random, guys, that's how it's going. What does that mean? Well, that means this. That means that right there. Since we're talking about x right now, guys, since we're talking about x, and we said v sub x squared bar plus v sub y squared bar plus v sub b squared bar, since they're equal, this is the same size as v sub x squared bar. That's the same size as v sub x squared bar. Divide by 3. You understand, ladies and gentlemen, that's true in the big scheme of things. That's true. It's also true v sub y squared. V sub y squared bar is equal to 1/3 v squared bar. V sub z squared bar equals 1/3 v squared bar. What is going on? I'll tell you. If this is true, and it is, we did already say, ladies and gentlemen, we did already deliver this speech. The derivation was there. We're just dealing with the y component, with the x component now, but we could be dealing with the z component. Even for that particle. That particle's got an x component of velocity. Also has a y component of velocity. Also has a z component of velocity. Let's talk. Yeah, we just said this guy right here is this. 1/3. Okay, let's put it in there then. Nm over d. That's neat. That's neat. You could take the 3 here, the 1/3, and let's talk about this for a little bit after we do this. Leave the m. Here's v squared. mv squared looks a lot like 1/2 mv squared kinetic energy. Remember how temperature and kinetic energy are so closely related? We're starting to see some stuff kind of creep into this whole thing. You could play this a bunch of ways. You could almost say, well, you definitely can say, what is going on here? That 1/3 means 1/3 is going in one direction, the other 1/3 is going in the other direction, and the other 1/3 is going in the other direction. And I only care about the 1/3 because it only hits whatever happens with the two walls that are on the x-axis. The same thing happens with the two walls that are up and down from each other and the two walls that are out toward you guys and out toward me. There's so much symmetry here, I just need force divided by distance. I don't need all the forces. If I do all the forces, I divide by all the areas. Well, it's going to be 6 times the force divided by 6 times the area. The 6's cancel out. If I just do the force on average on the wall divided by one wall, the same thing's happening to all the walls. That's one thing that comes into play. So they're saying all that. Yeah, okay, so what? So what? What else you want to say about it? This is the force on one of the walls. Period. It's the force on one of the walls. I guess it's indicative of what was going on over here. If you're careful about it. It's the same force. Yeah, it is the same force. What does that mean? I guess you can interpret it as saying everybody's x component at once plays a role in this, or 1/3 of the particles predominantly have everything hitting in the x direction. It's a neat interpretation. You can interpret that 1/3 of the particles are all going along the x-axis at any given time, on average. Another 1/3 of the particles are going in the z direction. And another 1/3 of the particles are going in the y direction. Solely in the x direction, 1/3 of them. Solely in the y direction, 1/3 of them. And solely in the z direction, 1/3 of them. That means their average velocities, 1/3 of them have average velocity going, bam, straight on in the x direction, back and forth. Another 1/3 have the same average velocity going up and down in the z direction, and another 1/3 have it going back and forth in the y direction. You can interpret it that way. Interesting. Full blast, all velocity, completely in one direction for 1/3 of them. The other 1/3 completely in a perpendicular direction to the initial direction, and the 1/3 is perpendicular to those two. X-axis, y-axis, and z-axis. 1/3 of them each are doing that. That's this interpretation. This one says all of them have an x component, which is on average 1/3 as big as the total. And all of them are going to go back and forth in the x direction. Yeah, all of them. What are you talking about? It's going to be a bigger number. No, because this is this is 1/3 the size. This is 1/3 the size of the big one. And that was right here. Wow. Interesting interpretation. Interesting interpretation on that. I'm not pretending to be in there when this is all happening, but it's happening. And mathematically, it holds up. Mathematically, it certainly holds up. The pressure is force divided by area. We're just doing one of the walls, guys. We already just said that. Here it's the force on one of the walls. It's going to be the same force on the other wall. One of the walls on the right side of the x-axis, one of the walls on the x-axis is going to have this force associated with it. The other wall, there's two walls on the x-axis, two walls on the y-axis, and two walls on the z-axis. Well, what's the total, how much force is this going on here? Yeah, if I double it, it's, as far as like magnitude of force, it's double. Yeah, I know, but it's double the area. So you're just talking about one of them. This happens, ladies and gentlemen, to every single wall. Every single one of the 6 walls, this happens to it. What's the force on that wall, guys? Didn't we say it was a square box? D by D by D. Well, the square portion is D squared. Equals. Here's F. Here's this. Go ahead and do it. F is, let's have a look. It is going to be, let me just kind of do it here. Let's take this. Let's maybe cut to the chase a little bit. That's D squared on the bottom. Take all this and divide it by D squared. You divide all this by D, you divide all of this by D squared. Divide all of this, F over A, this over A. All of this divided by D squared times D is D to the third. So basically that's where they're getting that. They're getting 1/3 ND cubed MV squared bar. Now we got to talk. May I ask you this question? D squared is the volume. N is N. Man, this thing is still staring at us right in the eye, man. This MV squared looks a lot like 1/2 MV squared. If you don't believe me, let's make it look like it. Tell you what I'm going to do. Multiply by 2 over 2. Multiply by 2 over 2. 2 on top, 2/3. Half here. Is it true? You know where I'm going, guys. Is it true that a half times 2/3 gets me back to 1/3? This is huge. This is immensely significant. I mean, all of it's some beautiful stuff these guys first did. I mean, they knew their stuff. And they confirm it. Experimentation confirms what they want to do in so much of this. The pressure is proportional to the number of molecules per unit volume and to the average translational kinetic energy of a molecule. Yeah. This is the average translational kinetic energy per molecule. The average translational kinetic energy per molecule is directly proportional to temperature. Didn't we say temperature, big temperature creates big pressure, everything else equal? With everything else not changed, big temperature creates big pressure. Small temperature, small pressure. All other things held equal. Tell me if this is not saying some of what we already said. I'm not even worried that the equals are here because they're all equal to each other. Absolutely. If there's a lot of particles per unit volume, remember, if the volume ain't big and you got a lot of particles in there, the number of particles per unit volume is a big number. If the average translational kinetic energy is big, big times big is big pressure. A lot of particles confined in a small volume, times a great amount of kinetic energy per particle, indicative of temperature. Didn't we say that pressure was inversely proportional to volume, directly proportional to translational kinetic energy, which is temperature, or closely related to temperature, absolute value temperature, and N is the number of particles. PV was equal to nRT. P was equal to nRT over V. It's a thing I said relatively long time ago in this discussion. The pressure is proportional to the number of molecules per unit volume and to the average translational kinetic energy of a molecule. That's of interest. Okay, we said a lot. Okay, so there's a lot being said here, guys. We got to talk. I mean, let's look at what we got over there. Guys, let me just make sure that I've got enough battery life here. I don't want to lose the audio on this. Okay, guys, I'm going to change batteries pretty soon. Ladies and gentlemen, let me just change batteries in case we get there may be an issue, there may not be. Let me pause this and let me come right back. Okay, hold on one second. We've got the stuff here. Give me 1 minute, please. All right, guys, thank you. Sorry about that. I just wanted to make sure the microphone's going to work. I need to replace the batteries here, so we're fine. All right, let's keep going. I raced a little bit. It's kind of a springboard to where to go now. We drew the conclusion in all that we've done up to this point. We drew this conclusion. We kind of started with pressure to begin with. It was something that we could measure more or less pretty tangibly. V is volume. Forgive the repetition of the symbolism, guys. Capital, I try to make it big, make capital V for volume. Okay, we've been here. We've done this. Why don't you multiply by capital V on each side? So it's starting to look like something familiar. Yeah, true. Didn't we say something earlier? We said a lot of things earlier. Among the things that we said earlier was this. We also said a lot. I mean, we said PV, this is no accident here. PV equals nRT. We said all of this. Absolute temperature, and average kinetic energy are all closely associated. All right, we know that. We know a lot. We've seen a lot. We've got the notes. Got this. You got that. True. If that's the case, well, I'm not saying anything too profound, guys. PV and PV are the same thing. That means this and that are equal to each other. The left sides are equal to each other. The right sides are equal to each other. Make a long story short. Man, that kinetic energy is not a joke. I mean, it's there. It's there. You're looking at it. What do you want to say? Well, let's say a couple things. I mean, let's solve for T. This has to be absolute This only works on an absolute temperature scale. Specifically, it works for the Kelvin temperature scale, given the numbers I already gave to you. If we constructed another, and we certainly could, if we constructed another temperature scale that was based on absolute zero, some kind of absolute zero. If we constructed another temperature scale based on absolute zero, all of this would still work. You just have that different constants would have to be brought into play. That's all. Divide by the product NK sub B. Divide by NK sub B on each side. The n's cancel when that happens. And you end up getting, you get 2/3. Let's see here. You already have the 2/3, right? Yeah, here's 2/3. The KB's right here. Here's the 2/3. Divide by KB on each side. Divide by N. Then you got this. That's the average kinetic energy per particle, ladies and gentlemen. The average kinetic energy per particle, not the sum of all the kinetic energies, the average kinetic energy per particle is directly proportional to the absolute value temperature. These guys are just constants. That's crazy. Why don't you solve for this guy? The 1/2 mv squared. What do you say you multiply by 3 kb over 2 on each side? Three kb over 2 on each side. There's a T there too, right? Yeah, there it is. That's for one particle. I want to know the total kinetic energy. Oh, yeah, you want to know the total kinetic energy? Multiply this guy by capital N and multiply that guy by capital N and see what happens. KE total is everybody. All right, on average, right? How many are there? We just said it was capital N. Really? Capital N, huh? Multiply by capital N over here, multiply by capital N over there. 3/2. Capital N, KBT. Wait, that looks awfully familiar. This NKBT looks like the NRT. There's just the 3/2 here. Yeah, big time. This NKBT is NRT. 3/2. Whoa. Yeah, we already said that. Remember, we said, how far back do you want to go? Okay, well, let's go here. I mean, heck, we're looking right at it. You don't have to go that far back. Look right here. Here's your PV. Here's this. What the heck, to not keep us in suspense, we know that PV also equals nRT. A claim we've made. It's pretty crazy. Yeah, sounds good to me. Let's talk. I mean, let's talk a bit. I guess you could say, let me see where kind of see where he went. I don't want to beat this thing up too badly, but the KE total, I'll put it in here and probably just erase it pretty quickly, but just to kind of talk about it, the KE total, nRT is PV. Pressure times volume times 3/2. Well, 3/2 is a constant. 3/2 is a constant. So 3/2 is a constant. Didn't we say that pressure is energy density, more or less? Pressure is the density of the energy in the sense that pressure is energy per volume. Energy per unit volume is pressure. Energy per unit volume is pressure times volume. This is energy or work. This is energy per unit volume times volume. You got energy. The amount of kinetic energy, ladies and gentlemen, is directly proportional to P times V. What am I saying? I'm saying if there's a container that has a tremendous amount of pressure and it's a big container, and the big container, the fact that it's so big does not dissipate that energy. You'd think once you make something a big container, there's not much room for there to be a lot of pressure. If it's a huge container, and it still has a lot of pressure, despite the fact that it's huge, if there's a huge amount of pressure, energy per unit volume, and there's a tremendous amount of volume and it's still there, pressure times volume is indicative of total energy present. That's believable. It's believable. It's similar back to we were doing Bernoulli's equation and talking about stuff. It's kind of, there's a reminiscence, I guess you could say, going on in that regard, huh? So, I don't really go there that much, but say, of interest, for a monatomic gas, translational kinetic energy is the only type of energy the molecules can have. For diatomic and polyatomic molecules, additional possibilities for energy storage are available in the vibration and rotation of the molecule. You might get a bigger number here. The coefficient here is going to tend to get bigger, but the nRT is going to stay. The nRT, which is PV, will stay, but this ratio, 3/2, if you go for a diatomic gas, it won't be 3/2, it'll be 5/2 or 7/2, depending what's going on with this. You could have the ratio here could be bigger, meaning there's more total energy. That energy is not translational kinetic energy. This is important, guys. Let me kind of say something here. The average translational kinetic energy is 3/2 kBt for one molecule. For all the molecules, it's 3/2 nkBt. Can I ask you a question? Is 3 times a half 3/2? In the x direction, nkBt times a half, this is the total kinetic energy associated that's occurring in the x direction. In the y direction, it's the same kinetic energy that's occurring. In the z direction, it's this kinetic energy that's occurring. Well, wait a minute. If I take, there's 3 dimensions, 3 of them. The average kinetic energy, the kinetic energy that is present in total, on average, is nkBt. In the x direction, it's 1/2. In the x direction, everything back and forth in the x direction, the total kinetic energy there is 1/2 nkBt. It's also 1/2 nkBt in the y direction. It's also 1/2 nkBt in the z direction. You multiply it by 3. This is the degrees of freedom. It's got the freedom to move along the x-axis, along the y-axis, and along the z-axis, if it's a monatomic molecule. If it's a diatomic molecule, it has not only that kind of freedom, but it also has another 1/2 nkBt as far as rotating in a particular way. And there's yet another way it can rotate, another 1/2 nkBt. And then if it's a diatomic molecule, it can vibrate, go in and out. And that means what? That means there's the vibrational energy as well. All the degrees of freedom share, all the total energy that's present is shared among all the degrees of freedom. And they kind of talk about that. They say, trying to think here how they actually wrote this. And they got different degrees of freedom here. Let me just see here. A full analysis of a given system is often complex. So in general, molar specific heats might be determined by experiments, you guys. What they say here for, let's say, a diatomic. There's different. Let me kind of not go very, very, very far into this, but in general, guys, if there's a lot of degrees of freedom, if the molecule is very complex, it can tumble in various ways. It can tumble in 2 directions, perhaps more. But I mean, at least for our diatomics, it can tumble 2 different ways, and it can also go one of 3 different. It can go any one of 3 different ways in the translational sense. That's where I wrote all this song and dance. That's where we got the 3/2. So it's got an equal amount of energy associated with movement in the x direction as it does with movement in the y direction, as it does with movement in the z direction. And if that's a monatomic gas, and that's all you got. That's all you have. It's a monatomic gas. If it's diatomic gas, it can also rotate in 2 different ways. And each one of those also has 1/2 n kBt. Each one of those has that. So you're not going to have 3 times a half. You're going to have 5 times a half. And then there's other considerations in different circumstances. But the equal partition theorem, there's this theorem that says basically the energy that is present will distribute itself equally in all of the available degrees of freedom that are associated with the state that it's in. If there are 7 different degrees of freedom, 3 of them being X direction motion, Y direction motion, X direction motion, Y direction, X direction motion, Y direction motion, and Z direction motion. 3 of them are that, 3 times a half, times the NKBT. Rotation, yeah. Oh yeah, also vibration. The compression and the out, that's another half and a half. That's 7. 7 different degrees of freedom that are available, let's say, in the circumstances that we find. 7 times a half is 7 halves, not 3 halves. So we'll cross those bridges as we need to cross those bridges. Notice, I don't care if it's 3 halves, 5 halves, or 7 halves, or anything else. Big brother in all this is T. That's and the number. The number of items present, if there's a lot of them present and there's a lot of temperature, you better believe there's a lot of energy. How could there not be a lot of energy if there's a lot of things, a lot of very, very many particles present? Small n is very big. Small n is a big number, many moles. Many moles means many particles. Many particles in great temperature, you know it's going to be a big. This right here just gives you a sense of how much energy's got to be present for all of this to happen. You cannot give a molecule a great amount of kinetic. You cannot give a molecule a great amount of translational kinetic energy. If it's a complex molecule, you have a hard time giving that complex molecule, those complex molecules, you have a hard time giving those complex molecules a tremendous amount of translational kinetic energy. You can do it, but you got to put a lot of energy into it because much of it will go to translational kinetic energy, other will go into rotational kinetic energy that can occur in various degrees of freedom, and also into vibrational energy. And all of it gets equally partitioned to do that. It's a big thing. So you can do it, but I'm going to need a lot more energy to give. I'm going to need a lot more energy to bring a complex gas to a very high temperature. I'm going to need a lot more energy to do that than I will for a monatomic gas, where I only have to worry about, hey, I give the energy, it all goes to kinetic energy, it'll show up in the temperature. It'll show up in the average translational kinetic energy. That's directly proportional to the temperature. If I try to do that with something that's more complicated, I got to give those things a lot of translational kinetic energy. Yeah, but a lot of that energy you put into it is going to get partitioned to rotation and to vibration that wasn't going on with the simpler monatomic gas. Okay? That was not going on with the simple monatomic gas. So anyway, that's something to kind of keep in mind. It's a lot to say, guys. I mean, there's a good amount here. They kind of go, let me get rid of this. You can always come back to it now. We've got it on the film, as we said. So there's temperature plays a huge role. There's no two ways about it. The amount of something there and the temperature, so forgive me, guys, I just messed this up a little bit. All right. Okay, so okay. So what? You see, we said what we said. Well, we said a lot. I mean, I definitely said a lot. And let's just say, as far as speeds are concerned, guys, we have said if it's a single particle on average, not all n of them now. Remember we said it was we were kind of here. N of them. Oh, wow, all of that, eh? Okay. And then we said that was the same as N kBT, absolute value temperature. Divide by big N on each side. That's just for him. Multiply by 2 and divide by M. Multiply by 2 and divide by M. VRMS is the square root of the average. Square root of the average of the squares. Okay, good enough for me. That's, why don't you square root both sides then? Yeah. Here's T again. It ain't leaving. Why is it inversely proportional to mass? Because if the thing is very massive, it ain't going very fast. It doesn't have to go very fast to have a great kinetic energy. It will have a great kinetic energy without going very fast because it's massive. So the less massive something is, and the higher the temperature, that is indicative of VRMS, which is roughly an average. It's a kind of average. And then they say, well, okay, what else is that? Well, we have how do you want to do this? You can do a couple things here. We could say that KB over small m is equal to R over NA. R over NA is KB, and here's M. So if you put 3 kBT over M, KB over M is R, KB over M, okay, this is KB over M, R over NA, small m, the mass of the molecule. R over all this is the same as that, okay. 3 is 3. T is T. Yeah, the mass of a single particle, time of Avogadro's number, is equal to the molar mass. That's the molar mass. So that becomes just another way to write it. They like to write things in a number of ways if they draw a blank. That's the molar mass. And that's this guy too. It's a lot there, guys. The crazy thing is, somebody could ask a question, and somebody could ask the question as follows. What if it's a sphere we're talking about? What if it's a cylinder that we're talking about? What if we're talking about something that's nowhere near as symmetric as a sphere or a cylinder, or nowhere near as symmetric as a rectangular box, or the great symmetry, like I said, not as symmetric as the great symmetry of a sphere or the great symmetry of a cube? Still works. The amount of particles, you could play a lot of the same mathematical tricks. Collisions are going to be, if the area, wherever the area hit, wherever the easiest way to look at it is, wherever on this, in this surface, there's a collision, there's an area. Any area A has a number of collisions called, I mean, I don't want to call it big N or small n, but it had, let's just say it has alpha number of collisions. In area A, an area capital A, any small area, capital A, in any kind of surface inside of it has no gravity or anything. It's just these stuff's just randomly flying around. They're equally likely to go anywhere. Gravity's not holding it down, nothing like that. Okay, everything's going straight. At any particular area, capital A, has alpha collisions in a time t. Any other area, capital A, which is the same number, any area called capital A has alpha number of collisions in a time period of t seconds. Area capital A has alpha number of collisions in a time period t. Another place in this surface, also with the same exact area, capital A, on average also has alpha number of collisions per time period t. Absolutely. You could also look at it kind of in a weird way. Is you could look at you could build columns pointing in the x direction. You could build columns, small columns, however small you want, all pointing in the x direction, and all of them encompass the entire area, or very close to it. If it's not good enough for you, make the columns even smaller. And it doesn't matter how big the columns are. If one column has an area, has a volume which is 10 times larger than the other one, it's not going to have 10 times the pressure. What are you talking about? 10 times the volume means 10 times the particles. Yeah, but it's also 10 times the area that's being hit. 10 times the force divided by 10 times the area is just force over area. 10F divided by 10A, 10F divided by 10A is F over A. F over A is the same as 10F divided by 10A. You say, okay, yeah, that's good, but what if the column is longer? Because it's got to reach further. It's such a non-symmetric surface. If the column is longer, let's say it is r times longer than the other column, that means there will be r times less collisions. If it's the same, let's say it's the same volume for all of them. Now let's make them the same volume, let's say. You say, okay, now what's going on? Well, if they're the same volume, but one's a long column and one's a short column, doesn't the short column going to have more collisions? Well, the short column is going to have a broader base. Its base is going to be r times broader, so if there's r times more collisions, the area is r times bigger. R times more collisions is r times more force. R times more force divided by r times the area, it's just force over area again. It's going to be more collisions because it's a shorter distance for them to travel. You could say that. But yeah, there's going to be more collisions, but it's more area. Why would there be more collisions? It's traveling r shorter. If the d is r times shorter, is 1 over r the distance of d, that means the time between collisions is going to be 1 over r times less. There's going to be r times more collisions. Yes, but the area is r times bigger. So you could even play it that way. I don't know how well I said that. Don't worry about it. It all balances out is kind of the moral to the story to this thing at the end of all that. All right. So that's that. I mean, there's some other stuff that can get said, I guess, and I'll see how I want to do it. I might do this in two videos, guys. Let me see exactly where I'm at, how long I've been talking, actually. Okay, so I got a little more time. I guess I could go. So anyway, here we go, guys. So let me give you some of the highlights without giving too great of a discussion of some of the stuff that can happen here. Let's talk about a few things that I think you'll find of interest regarding some of the thermodynamics that we know, you guys. I'm just trying to figure out. And there's some great books. There's some great books out there and some great stuff that gets done. Let me talk about it a little bit. I guess we can talk about things as we need to talk about them. Let me say a few things about some of the thermodynamics that's there. And I'm likely going to break this thing up a little bit, guys. I don't want to, I don't want to talk for 5 hours straight on this thing. We'll probably break it up just a little bit for tomorrow as well. But let me say a couple things here that I think can help you out. And we can kind of talk about some of the problems that I might do may repeat, but I think if they're good enough problems, it's good to kind of give them a look. Sometimes it's good to look at them more than once. I mean, it's not always the ideal way to go. Sometimes I think it's useful, though. If there's a lot of, we can give different perspectives on it each time. We'll see. I've got a few things in the works on this to look at some of these problems, see how you guys might feel about them. But we'll cross every bridge as we need to cross them, guys. Right now, we're not going to worry about it too much. There are I don't know how I manage it, but I always don't have a lot of chalk. The fact that I write like a baboon doesn't really help either, but okay, so let's look at this, guys. Let's look at a few things here. We've said stuff. I mean, we know some of this stuff by now. You know some of it in your sleep, I think. And I have this under the ideal gas law and some other stuff in Canvas as well. And we can always come back to it a little bit. But let me, again, this is stuff you've seen, stuff you know. I mean, we do know this, right? We know we were talking about it. We did it. Let's see here. Just make sure nothing crazy just happened here, guys. Last thing I want to do is put something up there like that. PV equals capital N KBT. Right. All right. So, et cetera, we talk. All right. When you want to heat something up and put amount of heat Q inside of it, let me stay rather liberal in my presentation here and not be very heavy on all of the specifics, but at least hopefully give us a little bit of a feeling for what we got to be doing here. If you want to put heat in something, and if you want to change temperature, is it intuitive enough, everybody? Is it intuitive enough for you? For me to say if you want to change the temperature of something in terms of absolute temperature scale. Now look, the difference in degrees Celsius and the difference in degrees Kelvin are identical. A rise of 10 Kelvin in temperature is equivalent to a rise in 10 degrees Celsius in temperature. A drop of 50 Kelvin in temperature is the same as a drop of 50 degrees Celsius in temperature. The more you want to change the kinetic energy, the more work has got to be put into it if you want to increase it. And if you want to take away kinetic energy, then you got to take away kinetic energy. If you want to drop temperature, one's going to be positive, one's going to be negative. Delta T, if it's big, you need a lot of Q. C is a constant, specific heat capacity, and M is the mass of the substance. Is this believable? To me, it is. If something is very, very massive and you want to change its temperature greatly, both of those mean you need a tremendous amount of heat put into it to change that mass, which is very massive, by a great amount of temperature. Very massive by a great amount of temperature. And that's a specific heat capacity. If you are not changing temperature, but you're changing phase, then it's plus or minus mass, well, the more massive something is, the harder it is to do something. If you want to melt it, it's got to be plus. You got to put a positive amount in. If you want to freeze it, you got to take away. You got to take away energy. You got to take away heat energy. That's mass, and that's a constant depending upon the substance. That's a constant depending upon the substance. We're talking about some boiling. Boil, condense. That's what they're saying here. Okay. So this is something that we might encounter if we encounter it. I mean, regardless of what I test you on, as we get into the semester doing stuff, guys, it's good to know this stuff. It's going to help you for a lot of things. Something expands. And again, the constant here, this is mass. The more massive something is, the more heat energy you need to take out, to freeze it, or to take out, to put in to boil it, or to take out to condense it, have it come down from a gaseous state to a liquid state, condense it. You got to take a lot of energy out, put a lot of energy in to make it boil. The more massive it is, the harder it is. Makes sense to me. This depends upon the substance under consideration. To melt something, yeah, there's a lot of it there, you need a lot to melt it. If there's a lot of it there, you need a lot to freeze it. You need to take a lot out. So this is what they mean by the Q, plus or minus. It's right here. A volume will expand by this coefficient called beta times the initial volume. The more volume you got, the more expansion there's going to be if you can actually make the temperature change. The greater the temperature change, the more expansion in volume is going to be. This beta is usually 3 times bigger about than alpha. And alpha is the linear expansion coefficient. Coefficient of voluminous expansion, coefficient of linear expansion. That comes from a calculus problem. If you were to cube something, the derivative of something cubed is 3 times something. So there's ways that can be viewed. We could look at. We'd have to look at it. But for right now, we're not worrying about that. We're saying, okay, they gave us this. It makes sense to me. The longer something is, if you can get it to change temperature, yeah, the length will change a lot more. A very, very long piece of steel, if its temperature is changed quite a bit, there's going to be a big difference. Proportionally speaking, it'll be the same. It may only expand by 10%. Yeah, 10% of a 100-meter steel beam, 10% of a 100-meter steel beam is 10 meters. 10 meters expansion. 10% of a 1-meter steel beam is only 10 centimeters. It'll expand the same percentage. A 1-meter steel beam under all the same circumstances. If it's 1 meter long, it's going to expand. Let's say it expands 10%. It'll expand 1/10 of a meter, 10 centimeters. What if it is 100 meters long? 10% is 10 meters, not 10 centimeters. It's still a 10% expansion. Same with the volume, same with the length. So watch out for that, okay? Okay, so we got that stuff. Okay. Kelvin's the one. Gets used so often they don't even put a sub K here. It's T sub C plus 273, 273.15. You got the Celsius temperature, add 273, you got Kelvin. A lot of times I write it like this. You can write a lot of stuff, guys, if you feel comfortable with what you're writing. Just don't, again, we got it, that what applies to me applies to you. We can't be careless. Mechanisms of heat transfer. It's talk about it really quickly. Again, within the context of doing these problems, guys, and I've got a lot of problems fully solved for everybody, within the context of doing these problems, I think the theory comes out as good as any lecture will give it to you, if not better. I mean, obviously you gotta know the basics. You can't walk into something, gee, I'm gonna walk to this, I'm gonna go to this particular country and I'm not gonna speak a word of the language, now I'm gonna learn it in the next hour. Well, it doesn't work that way. I mean, we gotta have a little bit of the basis to get there. And then from there, by application and experience, I think we get a little better at it. That's kind of the point. Well, they talk about mechanisms of heat transfer. And there's three big ones. They talk about conduction. And again, guys, I think various aspects of this stuff I've discussed elsewhere in one form or another, but I think there's nothing wrong with seeing this stuff again. Nothing wrong with it at all, I think. Conduction. If there is an area here, area A, and it's going over, it's area A here too, and it's going over a length L, and you got a temperature here of, let's say this is T hot, TH, and this right here is T cold, absolute value temperature. Here's T cold, here's T hot. Delta T is T hot minus T cold. Heat flows from hot to cold. We've got that. What does your gut tell you? I mean, my gut tells me this. It's easier for heat to flow if there's a large area in contact with the two heat reservoirs. There's one place where we're all over the place. It's in contact with something that's really hot, and the other place it's in contact with something that's really cold. And I want to see what's going to happen. Well, it's really cold over here to the far, it's really cold over here to the far right. It's really hot over here to the far left. So it's a very cold temperature, T sub C, and a very hot temperature, T sub H. I'm thinking the greater the difference between the two, if TH minus TC is very, very big, then delta T. Okay, this is, let me see how we can, that's TC, guys. Delta T, the bigger the delta T, the more tendency there's going to be, the greater the rate of energy flow from hot to cold, the greater the delta T is. The more area is in contact in both places, the greater the flow as well. But the longer the conduction has to travel, the longer the distance that it's got to travel for this domino effect to happen, the longer the distance, the harder it is. So it's directly proportional to delta T, directly proportional to A, but inversely proportional to L. That's what the science says. The rate at which heat is transferred, Q divided by delta T, or Q divided by T, or power, that's power. This is energy. Energy divided by time is power, same thing, is some constant. It's directly proportional to the area. The more area in contact, the more chance there is for you to transfer energy. So big area in contact means big transfer of energy. But the longer it is, it undoes it. It undoes it. You want L to be smaller. Smaller L is the better. It's inversely proportional to L, directly proportional to A, and directly proportional to delta T. And that's big. That's some big time stuff, guys. You can play games with this thing in such a way you can kind of make it, you can make it analogous to how electricity flows if you play it right. Okay. Not our business right now, but it's of interest. So that's conduction, you guys. That's the conduction they're talking about. And this is, look, nobody's moving that far. There's not really, hey, this atom right here ends up finding itself over there. That doesn't happen. It's kind of like the domino effect associated with the conduction of electricity in a sense. So it's a little different. It's a different dynamic. It's a different dynamic. Convection. I got it in my notes. Let me kind of like, rather than write the whole thing out for you, let me just say it. You can hear me say it, and you can look it up in the book and in my notes, where I have it fully written for you. Convection is the large-scale movement of heat. Convection is the large-scale movement. Convection, the large-scale movement of heat and mass, unlike conduction, where material oscillates and heat transfers. And heat transfers that way. Convection, large-scale movement of mass, substantial distances involved. This is different from conduction, where material does not move far, but stays close to equilibrium positions. During oscillation. So look, there's a lot of cold air in Canada right now. There's a lot of cold air in Siberia, and we end up, we'll get it. There are years we get it. We end up getting some of those weather systems. All this cold air from Siberia or from northern Canada ended up coming down to the northern part of the United States. That's convection. That's cold air coming en masse. It's no conduction here. It's all of it moving. Big pieces of air mass coming down to us, if you allow me to say it like that. Okay? So wholesale movement, large scale. Let me see. I'm trying to think of a good way to say this. Large scale, whatever that means. I mean, that could be relative too. Large scale movement. I'm blowing cold air into the apartment via the air conditioning system. Convection. Large scale movement of mass for that to happen. That's convection. Radiation. Everything gives off electromagnetic radiation, whether we realize it or not. There is some level of electromagnetic radiation being given off. And it contributes, and it has association with heat. Let me show you why. Let me show you how, at least, or at least talk about it a bit. Radiation. Here, electromagnetic radiation transfers heat energy at the speed of light. Q is heat energy per unit time. That's power. Sigma, epsilon, both constants. Area is A, area of exposure, Kelvin temperature taken to the fourth power. If something is absorbing electromagnetic radiation from outside of itself, and it's also giving electromagnetic radiation to itself. So it's absorbing electromagnetic radiation from the environment, and it's also giving electromagnetic radiation to the environment. There is a net difference. And the way that works, and we'll talk about that in a second here. Q over delta T is sigma epsilon A T of the environment. Let's say it's absorbing from the, let's say it absorbs more from the environment than it gives off, to the fourth power. That's the system. This thing, I think my, more to come on this, what the constants are. This is, yeah, and there's some different stuff here, guys. I've gone into, there's some problems with Dr. Kat. In the past, I don't think I gave something from chapter 20 from Dr. Katz's book. For you guys, they're in the calculus-based class, but I think I'm going to give some now. These days, we'll see. But there's some good problems here we can look at. We're horsing around with some of this stuff, you guys. What's going on here? This is Stefan Boltzmann's constant. It's a constant, straight up. This depends on the material, but it's a constant for a given material. Area, the more area of exposure, that means the more powers coming off of that with more area exposed. And the greater the temperature also means more, to the fourth power. So if you were to just double the Kelvin, if you were just to double the Kelvin temperature, 2 to the fourth is 16. 16 times the power if you double the Kelvin temperature. If you triple the Kelvin temperature, 81 times the power. 3 to the fourth is 81. More than 80 times the power if you triple the Kelvin temperature. So this is some of what's going on there, you guys. Related to some of the stuff we've been doing. So, and again, I think within the context of doing some of these problems, I think we really appreciate what we have to do at that point. Sorry about that, guys, here. Okay, but you see it. Again, within the context of some of these problems, I think we're going to be in pretty good shape, you guys, doing all this. So, there's that. I mean, some good problems you can look at. We'll cross all the bridges as we got to cross them, I guess you could say. There's a lot to be said. I'm kind of debating with myself. I think maybe start you guys up brand new on this. Let me just see where we are about on this. Okay. We're talking about some more thermodynamics, guys, and I think within the context, a lot of the problems that we want to do at that point, I think we'd be in pretty good shape. Again, there's two great books here: the Katz book for the calculus-based treatment of the physics, and the Survey book for the non-calc-based treatment of the physics. A lot of the processes are very, very similar, you guys. I'm going to say a few things here, and we'll see what we can say, which should make a lot of sense for us. And like I said, within the context of the problems that I'm planning to do for you guys, I think you'll be pretty well served on this stuff. All right, so we look at this, we know a lot. there's, I guess, the idea of temperature, there's just about no way it can be overemphasized in its importance. When we talk about absolute value temperature, how it's going to play a role, without being too bold here, just about everywhere you're looking at thermodynamic phenomenon, temperature is a huge consideration with what's taking place. Oftentimes what they do, they talk about a gas and they say the gas is compressed. Right, there's a volume, there's a pressure. Tell you what, let's make it so that we don't change the temperature of the gas, but we change something else. We'll change the pressure. By changing the volume, we'll change the pressure. If we can't, whatever. There's a number of things that we could possibly do. So with that in mind, you guys, let me try to put this together. Let me just put this. I'm going to come right back. I'm going to put it on break for 1 second, then throw a couple things on the board, and I think we're going to be in pretty good shape. Okay, hold on just 1 second. I'll just come right back. Okay, everyone, we're back. Take a little break, look at some of this stuff right here. Let's say a number of things, I guess you could say. There's this idea of internal energy. Internal energy is all the energy that's inside of a gas, let's say. Different definitions, I guess, come into play sometimes. Frequently, though, they're not talking about the chemical properties that are occurring, though in some places I've actually heard that said as well for internal energy. It becomes almost a subjective type statement. For our purposes, we're going to keep it at the microscopic level, but we're not going to worry too much about what would happen at the nuclear level if you're doing nuclear fusion, nuclear fission or nuclear fusion or something like that. It's another matter. Certainly that's energy, certainly it's internal, but I think they mean something different here when they're talking about the basic thermodynamics. At least the equations point in that direction. Typically, guys, remember when we said, I'm kind of digressing a little bit, but when we talked about the monatomic gas, any monatomic gas, and we found out the total kinetic energy that was present, well, that was its internal energy. They didn't talk about any kind of nuclear reaction going on. Well, there certainly is there are nuclear forces within each particle of the gas. They're not talking about that. So I get, the way it gets said in, I've heard different things in different literature, I guess you could say, read different things in different literature. For our purposes, if it's talking about a monatomic gas, remember we talked about the 3 different locations or directions, for lack of a better way to say it. Along the x-axis, along the y-axis, along the z-axis, it's 1/2 Nrt, right? 1/2 Nrt, but there's 3 of those degrees of freedom, so 3 times 1/2, 3 times 1/2 Nrt is 3/2 Nrt. This is the internal energy of a monatomic gas. If you were to heat up this monatomic gas, make capital T a bigger number, the internal energy would be bigger. If T is bigger, if you're not changing N and you make T, if you make T 5 times what the original T was, make it a size, make it an amount of temperature that is 5 times what it initially was, there'll be 5 times now the internal energy will have changed, and it'll be 5 times what it initially was for internal energy. The internal energy was associated with rotation, vibration, associated with compression and stretching, like springs, I guess, for the vibration aspect of the whole phenomenon. And it was also associated with rotation, being able to rotate one way or the other if it was more than a monatomic gas. If it's a monatomic gas, the vibration and the vibration and rotation don't come into play. It's just the 3 degrees of freedom associated with the 3 freedoms of translational kinetic energy. 3 times 1/2 Nrt is 3/2 Nrt. So If you were to keep everything the same, but have 10 times the number of moles in there and still keep the same temperature you originally had, the internal energy of that system would go up to a value that was 10 times what it originally was. If you left everything the same and made the temperature 5 times what it was initially, give it a size that's 5 times what it was initially, then U will be 5 times what it was initially for internal energy. So there's a lot to be said here. Change in internal energy is only going to occur here if you keep the same amount of material present. The only way you're going to change internal energy is by changing the temperature. That seems to be the way across the board. Even if there's other freedom that is allowed, rotation, vibration, everything that is allowed in that regard, temperature is always in the mix, is always there. Temperature is always there. If you don't change the temperature, you're not going to change the internal energy of the system. All other things kept the same. If you keep the temperature the same, all other things kept the same. If you keep the temperature the same, the internal energy does not change. The internal energy will change. All other things kept the same. If you change the temperature, you're going to change the internal energy. If you don't change anything else and you also don't change the temperature, you're not changing the internal energy. The U, the internal energy. The internal energy is oftentimes called E thermal. So the change in if you change the internal energy, you're changing the energy sub TH, the energy thermal. One book writes it delta ETH, the other one writes it delta U. Just wanted to tell you they're the same thing. Okay. If you're talking about the Survey book or the Katz book, there's a little bit of a difference there, but not much. The change in internal energy is equal to the amount of heat that you either put into or take out of the system, and also equal to the work that you either do to the system or you have the system do to the environment. If work is done on the environment, if you were to, there's a lot here, guys. I mean, the big thing here. Let me keep it with the delta U, but if you're more comfortable with the delta ETH, keep that too. Doesn't matter. The big thing is, with that right there, you guys, if you were not changing the internal energy of the system, but let's say you had the system do work on the environment, then it's lost internal energy. Yeah, but you can make up for it by transferring heat into the environment. So if there was no delta U that occurred, you could put heat, if you did work to the outside, well, the internal energy that's inside the system ended up doing work to the outside, but if you add heat to it to compensate for what was done, there's no change in the internal energy. And there's different ideas of where this thing can go and how this thing can be written out, you guys, when they do it. So let me see here. Changing chalk a little bit too, guys, here if I can. So anyway, some of the stuff that we're trying to say here. This is big time important. The first law of thermodynamics, and we can use it to solve a lot of the problems that we're doing. There are thermal processes in gases, and there's 4 major ones. There are isobaric properties called constant pressure. Isobaric, from the Greek word Greek words, iso means equal. Baric from the Greek word varos. Varos is weight. So equal weight. There's an equal amount of weight on the system. The system, the pressure that's inside the system won't change. Let's say you've got, there's a big cylinder and there's a piston, and you put on the piston. The piston has a total mass of 500 kilograms on it. Which has a weight of nearly 5,000 newtons. You don't change that at all. If you heat up the gas, what happens? The collisions are more violent. There's a pressure initially, and then it rises. It does work. It does work on the environment by picking up the piston. When it picks up the piston, the pressure stabilizes, and the pressure is the same as it was initially. Yeah, how could that be? Well, yeah, I put heat into this thing. I did work, but in the end, the pressure Because it got picked up, it's going at a constant pressure. See, the weight didn't change. You didn't put more weight on this thing. You're just moving it because you heated it up. So, isobaric from isovaros. Isovaros, same weight on it. There's a constant pressure for isobaric process, and we'll talk about that. There's an adiabatic process. No thermal energy transfer, either in or out. Q equals 0. See, you're going basically with, this is kind of the one they're working with across the board with this stuff, guys. The delta U equals Q plus W. No thermal energy transfer. Q equals 0. Adiabatic, aviavatikos. Avia or via means through. Avia means not through. Vatikos, I think something moving. There's nothing moving through. Nothing moving into this, nothing moving out to this in terms of thermal energy. So no thermal energy transfer, Q equals 0. Q equals 0 is an adiabatic process. Isovaros means constant pressure. We'll talk about that. We'll talk about adiabatic as well a little bit more. Isovolumetric, also known as isochoric. Isochorikos. Isochorikos. Choros is a space. Isochorikos is an equal space. The space doesn't change. The volume doesn't change. That's isovolumetric. Isothermal, thermos, heat, or temperature. Temperature is a better word for it. Isothermal, equal temperature. So let me come back to isovolumetric, isochoric. For an isochoric process, there has to be a movement of the piston for there to be work done. If the piston doesn't move either in or out, the volume doesn't change. But if there's no movement of the piston, force times distance is where we get work. Force times distance is where we get work. If the piston doesn't move, there's no distance traversed with the force that's being exerted. Force times distance is work. If no distance is traversed, no volume is changed. Constant volume corresponds to no work being done. If the piston doesn't move, force times distance is work. If no distance traveled, no work done. That means delta U equals Q. In other words, if there's no work done right here, no work done, the delta U equals Q. For isochoric. Isothermal, it's a constant temperature corresponding to delta U equals 0. If the temperature is not changing, you're not changing the internal energy of the system. That's a big thing. If the temperature's not changing, you got this going on. What does that mean? Man, if you do some work to the environment, you better be, then it's negative work done to the environment. Moving the piston outward is negative work done to the gas. It's positive work done to the environment, but negative work done to the gas. If negative work is done to the gas, you better be putting heat in there to make that thing be able to make a move. And then the delta U doesn't change. The internal energy stays where it's at. There is no change in internal energy if there is no change in temperature. There's no change in, and that's what I said very, very early on, guys. I use the monatomic gas as the example, but it generally holds throughout the board regarding what's out there. Regarding what we have, regarding what the mathematics tells us, if T does not change in terms of absolute temperature, if T does not change, U does not change. This is a simple example of a monatomic gas, but for any kind of gas, if you don't change T, you're not changing its internal energy. And that's what they're saying right here. Constant temperature corresponds to no change in the internal energy. If you don't change the volume, you're not doing any work. So, like I said, for isothermal, delta U is equal to 0. So maybe it's easier if we write them out, guys. Let me, so for delta U equals 0, we already kind of said that. We got delta U equals Q plus W. Let me just write it that way. The books are pretty clear. I'm using delta U, guys. In one of the books, again, they use delta ETH. It means the same thing, okay? Got this right here. We're going with this. So, man, if you're doing work to the environment, a number of ways you can write it. Q is going to be equal to, if you're doing work to the environment, that's positive work to the environment, but negative work to you, negative work to the system. The negative work of the system times -1, the negative of the negative work of the system is the amount of heat that you had to put in there for this to work out. So these signs can get a little messy. If you're doing work on the environment, that's positive work done on the environment, but that's negative work done on the gas. If work is done on the gas, that's positive work done on the gas, but negative work done on the environment. So basically what you're saying is, the work does, if a gas expands, the gas does positive work on the environment, but negative work on itself. If the environment compresses the gas, the environment has done positive. The environment has done positive work, but the gas has done negative work. So it's a hard one to call here, guys. How you actually want to say this? You're saying if you do. Negative work was done to the gas when it expands, and positive work is done to the gas when it's compressed. So if you compress this thing, you do positive work on it, you're going to have heat transfer out of there for this to remain zero. If you do negative work on the gas, in other words, have the gas do work on the environment, you got to bring heat in there for this to remain zero. So though this can get a little confusing otherwise, but basically, Q is positive when it goes in, it's negative when it goes out. W is positive when you do work on the gas, and negative when the gas does work on the environment. So you gotta be careful. So this is what they're saying for the isothermal. It's pretty big stuff, and like I said, is kind of maybe why I needed to take a little bit of a time out on this. To come right here. To come right there with that, and that's, like I said, we said that early on in the special circumstances right there. So, and again, this is kept in mind when they tell us enough things. Can we use this formula? The first law of thermodynamics, can we use it and do something with it? Well, yeah, I'm here. There's a lot I can do, depending what kind of problem I'm being asked how to do something. Here they're saying essentially that there's constant volume. It corresponds to no work being done. For there to be work done, you guys, remember, there's a lot that goes on here. I guess you could say, let me not say too much maybe, but let me say enough. I mean, if there's a constant volume, the piston ain't moving. And force times distance is work, and if the distance is 0, it ain't moving. F times 0, if the distance is 0, it ain't moving. That's no work. If it's no work, we're talking about delta U is Q plus W. In this case, Q is equal to 0. Yeah, they're going right here. And let's see here. I mean, if I am going to take heat out of the system, it's going to transfer out of there. I'm going to somehow transfer heat out of the system. I am going to lose internal energy. If I put heat into the system, I'm going to increase internal energy. It's that simple. There's no thermal energy transfer, adiabatic process. basically, if there's no thermal energy transfer, you're talking about a situation of no thermal energy transfer, Q is equal to 0. Any work you do on the system, if you're not going to bring heat into the system nor take heat out of the system, well, then what? I'm not letting heat leave the system. I'm not letting heat get into the system. What's there is there. So Q is 0. Nothing went in, nothing came out. The change in internal energy, is going to be equal to the work. If you do positive work on the gas, compress the gas or something like that, if you do positive work on it, you're going to increase its internal energy. If you have the gas itself do work to the environment, the gas does positive work on the environment, negative work on itself, you're going to lose internal energy. The fact that you let that piston expand, it loses internal energy. The internal energy is going to get lost. And that's what they're saying on something like that. So on and so forth. So you got something like this. We'll come back to it. Isobaric is constant pressure. So, and let me kind of look at a couple ways that they look at this, and we'll see what we can say about it. I guess a big thing to put here when you talk about isobaric, if you're not going to, and this is not necessarily the case. I mean, you could have P change. Can I ask you guys a question at least? I guess you could say, let's see exactly a good way to maybe talk about this. Okay, I'm going to come back to the isothermal process as well, guys. As far as the isobaric process is concerned, there are things that go on. I don't want to get too involved with the positive and negative of this thing. Do you guys, there's potentially a lot you can do here. Can I just say this? Are we believing with an isobaric process that work is equal to force times distance? A force acting through a distance. We remember that force over area, that's pressure. Area times distance, force over area, that'll be FD. Well, what's going on here? There's got to be a change in this in a sense. This is a change in volume, and this is pressure. I'm not worried about the positive and negative right now. We can talk about that. Pressure equals delta V. Pressure equals delta V. What does that mean? Well, a constant pressure applied over a volume like this, is that true? Yeah, you sort of see it. If the D is going to change, bam, that'll go. You got F times D, it'll work. The negative or positive is not a big deal. The work that I put into a gas is if I put a pressure and I move, if I take a pressure and I compress the gas, I'm doing work on the gas. If I let the gas do work, that's, again, we're talking about the positive and negative work, but the quantity, the amount is P dV, P delta V, okay? So, again, I think when we tinker with it, I think that the problems themselves are gonna yield a lot when we talk about this. I just want to give a little bit of an introduction on it. The fascinating thing about the isothermal, keep a constant temperature, and you got this right here. There is and how much work you would do. I mean, I guess you could say, how would that change? Just running out of room, guys, a little bit. Okay, we talked about this, delta U equals Q plus W. As far as the isohoric is concerned, I'm going to have to erase a little bit more eventually, guys, but let's just go through a few of these. What's going on? I mean, you got a constant pressure, this happens. You can basically say, for an you're saying that, recall that in an isobaric process, the pressure remains constant as the gas expands or is compressed. Okay, let's say we compress something, and if we were to compress something and the pressure remains constant, man, something's got to happen to the internal energy. The internal energy's got to change. It's got to lose heat for the pressure not to act up, for the pressure not to want to come back at us. Same thing if it expands, you got to put something in there. If you're going to expand something and keep the pressure the same, you got to put heat into the system. You've got to increase, somehow there's got to be heat going into the system for that to be the case. So let's see what they're saying here, guys. An expanding gas does work on its environment. P equals delta V. As previously discussed, the magnitude of work on the gas is just the area under the curve, all this stuff. The work done by a gas on its environment must come at the expense in change in internal energy. If you're going to do work on the environment, you're going to lose internal energy. So to keep the internal energy unchanged, you got to put Q, you got to put heat energy into the thing. Same thing if you compress something, you're increasing its internal energy. If you don't want it to change, you got to take heat out of there. And that's where that whole idea of this. You're going to see this in a lot of the stuff that we deal with. So with that in mind, let me try to exactly kind of give you a decent look on this thing. So, like I said, the work done by the gas on its environment must come at the expense of change in internal energy, because the change in internal energy of an ideal gas is given by something there. I don't want to even write what they had said there, guys. I think it's going to be a little more confusing than helpful. Expanding volume and decreasing temperature means the pressure must also decrease, in conformity with the ideal gas law. Consequently, the only way such a process can remain at constant pressure is thermal energy is transferred into the gas, you guys. So, I'll try to make kind of a long story short here on this. When they talk about the isobaric process here, if you're going to do something like this, Q is going to be delta U minus W. It's as simple as that when you're doing something like that. So that means vis-a-vis this thing, guys, saying if there is a decrease in internal energy, the thing, I think it's said a lot better in a different manner, I guess you could say. If you do work on the gas, positive work on the gas, you've got to lose heat from there for delta U not to change. And so here it gets a little messy when you do something like this. If you were to make this happen, if you actually did work on the gas, you'd have to make it so that the change in energy, whatever was lost here, minus the amount of work that you did on the environment, or the amount of work that you did on the gas, minus is plus. This work plus the change in delta U will be Q. So I think this is true. I think it's just more easily visualized, guys, when we leave it like this and then kind of make this game work. The way this is going to happen here, so we say, just don't want to say the wrong thing here, guys. Let me kind of look at it a little bit more. Consequently, the only way a process can remain at constant pressure is if thermal energy is transferred into the gas by heat. That's if it's coming out, rearranging the first law. So essentially, for the amount of heat that you'd put in there, I just don't, the negative signs are a real issue here, guys. The Q would be delta U minus W. Yeah, the minus signs are a real hassle, and then go ahead and write it again, right? It's saying delta U plus P delta V. So if you increased volume, the work that was done in the environment, for that to be able to occur is whatever the change in energy is, you'd have to add Q. So for that to take place is, so in other words, if thermal energy Q is transferred into gas by heat, so we have this right here. Consequently, the only way expanding volume and decreasing temperature means the pressure must also decrease. In conformity with the ideal gas law, consequently, the only way such a process can remain at constant pressure is thermal energy is transferred into the gas by heat. This will be a positive thing. So this has got to be something that in totality is going to be more than that. This guy right here will tell you. If it's going to do that, that much heat has to go in there if the delta U wasn't going to change, let's say. Okay. Let me, again, I think when we do the problems, I think it's a little more straightforward than the actual theory behind it. What they're saying essentially is this. This right here adds to the whole situation. And what happens is if this guy right here is, remember we said Nrt, U was Nrt, so du is Nr delta T. And this right here, to do that right here, so that we said it's going to be 3/2 Nr delta T. And this right here, is it true, guys, that the pressure that we would get here, let's say P, I'm trying to think of a good way to say this. The pressure is constant, so we would say I think the only way they could change it is this. Remember, we're going to say here the pressure is constant. So if we're saying PV, don't know where to start with this sometimes, I guess. If you've got V is nRT over P. And we talked about W being this. I'm sorry, guys, I don't want to erase any of it. But let me... V is this. Let's talk. I mean, everybody agrees. Everybody agrees with that. Let's divide by P on each side. You got this. Do you agree that if I ain't going to change the pressure, it's isobaric, it's an isobaric process, so the pressure will not change. The amount of material in there will not change, and R will not change. The only way I can change delta V is if the temperature changes somehow. If the temperature increases, volume is going to get bigger. If the temperature decreases, volume is going to get smaller. I don't want to get, so we got this. So wait a minute. P delta V is going to be P Nr delta T over P. The P's cancel. P delta V. The work done conveniently comes out to Nr delta T. P delta V is Nr delta T. Wait a minute. If this is, if we said this guy is 3/2 Nr delta T, the only way you're going to change internal energy is if you change the temperature. There's got to be a delta T. The only way you're going to change a delta V if pressure's constant and the amount of particles remain constant, and R, of course, is constant. If N, R, and P are constant, the only way you're going to change delta V is by changing temperature. What happens? You increase the temperature, volume increases. Decrease the temperature, volume decreases. So we can do stuff. There's stuff we can do. Well, yeah, okay, that's delta V. P delta V is P delta V. The P's cancel, and you're down to here. Wait a minute. Isn't Nr delta T the same as 2 over 2? Isn't Nr delta T the same as 2 over 2 Nr delta T? It's harder for you to change the temperature of a gas that is doing work while you're trying to change its temperature. That's why this 5/2 is a bigger thing right here. And similar stuff, similar arguments can happen when you're talking about gases. It all kind of stems from right about here. It all kind of like, this is the argument we were doing a while back to look at those collisions. What's going on here? Well, yeah, we did all that, and then we got to this guy, PV equals NR. PV equals NRT. PV equals NRT, then I can horse around with that right there. But PV equals NRT, from here, it's much more difficult for me to change. For me to you know, how much heat do I have to put into something to change its temperature? I'll tell you what, if you're not making a piston move, you only need to put this much in there. If, you know, assuming it's an ideal gas. If it's an ideal gas, that's all I got to put in there to change its to change its internal energy. This will make the internal energy change, and for me to change, how much heat do I got to put in there to change its internal energy when no work is being done? That much heat. How much work do I got to put in there to change its internal energy by the same amount, but work's being done? You got to change the internal energy and you got to do the work. It's a lot harder. You got to put more heat in there. If you're planning to change the temperature, and changing the temperature means you're changing the internal energy. The only criteria for internal energy is the temperature. If you're changing the temperature, you're changing its internal energy. Great. But you're also doing work. So you're not just doing 3/2 Nr delta T to change the internal energy of that monatomic gas when it's an isochoric process. If it were an isochoric process, if it were an isochoric process. It's not. This is all you would do if you weren't doing any work. If you kept that piston fixed, you could change the temperature by delta T by putting this much heat energy in there. Yeah, if you want to change the temperature of the gas by this much and have its internal energy change by this much, yeah, you can do it, but it ain't going to take only this much work. This will change the internal energy, and this will do the work. And this will do the work that is being done. Earlier, you weren't doing any work, so it's got to be a bigger number to get the Q. They say it in kind of a weird way. At least in my judgment, it sometimes gets discussed in a little different way. But that's the way I want to talk about it. And so on and so forth. I mean, the big thing is know what these benchmarks are. Benchmark for isobaric, benchmark for isobaric, benchmark for adiabatic, benchmark for isochoric, isovolumetric, benchmark for isothermal. And then when we look at the do's and don'ts, we look at what the when we look at how everybody relates to this, in terms of energy, in terms of heat, in terms of work, in terms of heat energy put in or coming out, work going in or going out, change in internal, how is the internal energy affected? What are the criteria? What are they asking you here as far as what the rules are? If that's the case, let me finish this up, guys. And again, the big thing is, let's look at the benchmarks. Let's look at the benchmarks, milestones, goalposts, whatever. The main things they're saying here, and can we then take this guy, delta U, delta U equals Q plus W. Can we do stuff with it? Can you remember that W is P delta V? If nobody's moving, there's no D. If there's no change in volume, there's no D, there's no work being done. And they talk about various things. Isothermal process. So temperature doesn't change. So if the temperature does not change, when the volume changes, what's going on here? So let's kind of come back to this thing. During an isothermal process, and I don't want to erase too much of this. Let's just erase what I got here and then kind of start it over. For the isothermal, some of the main discussion pertaining to that. Now, for isothermal, so for an isothermal process, you guys, we're saying that the T doesn't change. Well, if the T doesn't change, the delta U doesn't change. The only way, the sole criteria of internal energy, for our purposes, the way they have it defined here, we're not talking about nuclear reactions and other things. They're just saying, hey, look, let's make this simple. Let's look at this in sort of not quite a very, very microscopic way, but kind of at a very, very small level. Let's kind of look at it macroscopically, if that's allow me that. At a microscopic level, let's kind of be macroscopic. Let's see what's going on with the particles, how they hit, what work they're doing, what changes in temperatures and pressure and volumes take place. How are we changing the internal energy? The internal energy for the criteria that we have set forward. We're not talking about chemical reactions right now. We're not talking about nuclear reactions right now. But like I said, in different books, they say different things. So watch out how they say that. They kind of give the broad, I've seen the broad definition of internal energy to include chemical bonds, nuclear bonds, everything. All the matter that's there, what's its internal energy? I guess you could define it that way. In the mathematics for these particular types of problems, they make it a little more, I can say the word generic, or they make it a little simpler. They say, okay, let's look at this in terms of the collisions that are taking place, and let's stay at that. Let's see how these billiard balls are flying all over the place and how they're acting and what we can say about internal energy. Well, we know that internal energy, based on what I've said more or less a number of times, you guys, internal energy is hugely determined by absolute value temperature. If you keep everything else the same, and if you keep everything else the same, volume, pressure, whatever, the whole thing, if you keep everything the same, the amount of particles that are present, and you don't change the temperature, and everything else that is relevant to this is kept the same, and you also don't change the temperature, you've not changed the internal energy. So delta U is equal to 0 in an isothermal problem. What does that mean? Well, if delta U is equal to 0, 0 equals Q plus W. What does that mean? That means if you put heat into the system, the heat's going to go directly to doing work to the environment. If you take heat out of the system, then the environment will do work on the gas. If you take heat out of the system, the environment will compress the gas and keep the internal energy the same, unchanged. If you take heat out of the system, work will be done by the environment to to keep the delta U equal to 0. No change in the internal energy. If you take Q out of the environment, if you take Q out of the container, if you take heat, get heat out of there, take heat out of there, work will be done by the environment on the gas that's in the container. If you put heat into the container, then the piston will expand. That extra heat you put in there will power the piston. It'll power the piston. So in terms of magnitude, Q equals W in terms of magnitude. This negative W can get a little confusing, as I've kind of mentioned before. So what are they trying to say here, guys? Well, I mean, we kind of just said what we said. We can say, and they don't do this well. I mean, or at least I don't. I'll tell you what, I'm going to do it. There's a number of ways you can look at it. This is more of a calculus background to it. For a constant temperature ideal gas, we all know all right, guys, let's talk a bit. I mean, forgive me, guys. There's some chalk works better than others, but PV equals Nrt. All right, we've delivered that speech. I don't even know how many times. I am not making a definitive statement regarding what the pressure is. I will say this, I'll sort of make a definitive statement. Pressure is equal to Nrt over V. If you do not change the amount of material that's inside the cylinder, and R, of course, does not change, and the temperature is isothermal. This is, guys, I'm coming from way over there now. I'm doing the isothermal problem now, right? Isothermal. This is all isothermal. If N, the amount of material that's present is unchanged, common occurrence, N is not changed, capital N is not changed, which means small n is not changed, R is a constant, not changed, T is isothermal, not changed, V will change. How will it change? That depends. It might not change at all. If V doesn't change at all, there's no work done. End of the story. Because no distance. We already talked about that in the isohoric process. In the volumetric we already said that's going to be an issue. There's no work. Work's equal to 0. True. Yeah, pressure's going to change. Pressure's going to change if the pressure will increase if the volume gets smaller. That sounds good to me. If V gets smaller, pressure will change. Yeah, if V gets smaller, pressure will go up. If everything else is the same, Nrt, N is a constant, R is a constant, T is a constant. It's an isothermal process. It's isothermal. Okay, so if it's isothermal, yeah, pressure is going to increase. If V gets smaller, P gets bigger. If V gets bigger, P gets smaller. Okay, they're inversely related to each other. We're not going to worry too much on that. We know, say we just do it. Now, those of you with a calculus background, you're going to follow this. Those who don't, you're going to see the answer that's in the survey book. And this is how they got it. No big deal. No big deal. Take a couple minutes. The amount of work, man, is positive and negative is more irritating than anything, I think. The amount of work is P delta V. Yeah, I know, the pressure changes though. This ain't a joke. The pressure changes. Pressure's a function, so P delta V, yeah, that kind of works. you're better off saying the differential element of work is the function P, which changes, times delta V. Let's, I don't want to erase this stuff, guys. If they're up there, they're up there. But, I mean, you can always go back and look at it. Just make sure we got this. We got to here. If you integrate, it's going to be the integral of all this stuff. It's going to be the integral of this. It's going to be the integral from an initial volume to a final volume. PdV, time out. I don't know how good this shows up, guys. All right, maybe a little easier to look at. That's the big one right there. That's how it's going to work. Okay, if P is this guy, Nr all right, let's try this again here. It's Nrt over V dV. What's that? Well, let's go up here. Nrt, that's a constant. For our circumstances, that's isothermal. Isothermal. That's isothermal. That's a constant, and the amount of material that's gone in or out is zero. The amount of particles remains unchanged, R remains unchanged, T remains unchanged. Well, this logarithmic thing is all over the place, guys. If we're looking at this is the key to the whole thing right here, guys. Right there. When you do the integral dV over V, that's volume. You do the integral dV over V, it's ln V. ln V between these two limits is ln VF minus ln VI. Nrt, and you guys with the Survey book, that's where it's coming from. You guys not in the Survey book, this is where it's coming from. I mean, so it's good to know it. ln VF over VI. What does that mean? Well, it means a lot of stuff. It ain't no big deal. This negative thing is, you've heard me enough times, guys. You've heard me say this enough times. Kind of an arbitrary thing. If VF is big and VI is small, this is a positive ratio. Well, it's not only a positive ratio, it's a positive ratio bigger than, it's always a positive ratio as far as we're concerned. But this is a big number, that's a small number. Big divided by, positive big divided by positive small is a number bigger than 1. ln of a number bigger than 1 is a positive number. Positive work was done to the environment. I get the way this gets written. It can get a little touchy, guys. Is if you put a negative or a positive, it doesn't really amount to a hill of beans. The work under consideration is the environment. The work that I did to the environment is positive if I expanded the volume. If I did not expand the volume, but the final volume has contracted compared to the initial volume. If this is small and this is big, this is a negative number. The environment well, I mean, the environment did positive. The gas did negative work. It gets this positive and negative is kind of an issue, guys. I can tell you this much: the absolute value is always going to work out. You just got to remember who's doing what. Basically, if VF is big, if you're all positive numbers, if VF is big and VI is small, big divided by small is a number bigger than 1. Ln of a number bigger than 1 is positive. Multiply all the way across, you get a positive answer. In other words, the gas did positive work on the environment. The environment, I mean, so the gas did work to the environment did negative work to the gas. If it goes the other way around, if VF is small and this guy's big, small divided by big is a number less than 1. Ln of a number less than 1 is negative. Negative times this will mean that the environment did positive work. The gas did negative work. It gets a little touchy. The big thing here, guys, P delta V or something close to it, when you do calculus, you're getting to here. And the absolute value of this is spot on. Just know that the gas does positive work to the environment. The environment does negative work to the gas if the gas pushes this thing out. If the environment does positive work to the gas, and it does, the gas in essence is doing negative work against the environment. It's trying to stop being compressed, so it's doing negative work. If it pushes out, it's doing positive work to the environment. And that kind of flips, like I said, if the gas is being compressed, the environment is doing positive work. Okay. So on and so forth. Again, the absolute values kind of win the day, you guys. Don't get too hung up on negative and positive. The magnitude, as long as you know that when a gas expands, it's doing positive work to the environment. And the environment's doing negative work to the gas. If a gas does work to the environment and expands, it's doing positive work to the environment, and the environment's doing negative work trying to stop it from doing what it's doing. If the environment compresses a gas, it's doing positive work to the gas, and that's where Q is. That's where the whole situation, the work is positive done onto the gas by the environment. The environment does positive work. And the gas itself is doing negative work to prevent. The absolute values are all going to be there, guys. So don't be losing a whole lot of sleep on that. You could easily put a negative in front of this thing, depending what language you want to speak. The big thing that wins the day here is what are the absolute values telling us, and how comfortable are we with what is happening there. Okay, that's about all I wanted to say for thermodynamics regarding this stuff. I'm going to try to knock out some of the problems. I think that's going to say a lot. I think it's going to help us a lot when we do it. Okay. Thank you very much for your time, guys. We'll talk. Bye now.